Great. So we'll continue from where we left off yesterday. Just a quick reminder. So what we were doing was local testing of Reed-Muller codes, and we confined ourselves to the three-dimensional setting. Already results are non-trivial. It'll take a fair bit of work to sort of do this carefully. And the test was very simple. We picked a plane pi uniformly at random from FQ cube, and we accept if the restriction of f to this plane is a degree k bivariate polynomial. And what we would like to show, and the main theorem that we would like to show is that, so clearly, I mean, if f happens to be a low degree polynomial, this test will pass with probability 1. What we wanted to show was that if f is far from every degree k trivariate, then this test will catch it. It will reject with some decent probability. And the main theorem that I haven't written here, but let me say what it was. We were sort of trying to prove the counterpositive. We would like to show that if the test passes with probability 1 minus epsilon, then there is a degree k trivariate that agrees with f on at least 1 minus, say, 100 epsilon fraction of all inputs. So that's the theorem that we were building up to. And I said yesterday that there are sort of two main steps in the proof. The first step is going to be to show that there is a large collection of planes that are pairwise consistent with each other. So sort of a clean way of saying that is the following. So suppose G sub pi is the degree k bivariate equal to f restricted to pi for planes pi for which such a thing exists. Let's look at the graph G, where the vertex set is the set of all planes and two planes are adjacent to each other if G sub pi and the bivariate polynomials on them are consistent with each other, meaning they agree on pi intersect sigma. If the planes don't intersect, then they are vacuously consistent. Okay, so the first step, the first part of the proof will try to show that this graph G contains a clique of large size. So it contains a clique of size 1 minus 10 epsilon times the size of V. In the second part of the proof, we will show that we'll get our hands on a trivariate polynomial P such that on all of these, all the planes in this clique, the restriction of this trivariate to the plane is equal to G sub pi. So this will get our hands on a trivariate degree k polynomial that's consistent with the bivariates on all the planes in the clique. And we sort of hand waved through it yesterday, but once you have such a large agreement, so this trivariate P is consistent with so many of the planes in the graph, this will imply that it's consistent with a lot of points. It's consistent with f on a lot of points. So that part we sort of we talked about yesterday. I'm not going to. I'm going to focus on this. So there are two steps to be proven. The first is to show that the graph G contains a large clique. The second is to show that there is a low degree polynomial P that agrees with the plane polynomial on every plane in the clique. So let's start with the first part and then we'll get to the second part. We briefly talked about how the first part is going to go. The main claim here is to show that if we take a pair of planes, pi and sigma, that are inconsistent with each other, then we want to claim that at least one of them must be inconsistent with many, many other planes in the graph. Okay. And then this gives a natural way of defining a clique. So we can just take so the fact that one of pi or sigma is inconsistent with at least these many vertices tells us that its degree is roughly about half of 1 minus k over q. That's its fractional degree. But the average degree in this graph is super high. The test passes with probability 1 minus epsilon. So the average degree in this graph is around 1 minus 2 epsilon. And so we can pick, so the clique will be the set of all vertices of degrees somewhat larger than whatever is given by this claim. Clearly, these vertices form a clique because if they did not, then there was an inconsistent pair and its degree would be small. We have to argue that the number of such vertices is large, but intuitively that should be clear. So maybe one way of seeing this is that this graph E has large density. So let's think of the complement of this graph. In the complement of this graph, the average degree is about 2 epsilon times the size of V. In the degree of these vertices in the complement of the graph is about half times the size of V. So Markov will tell you that the fraction of vertices with degree as large as half is going to be something like 1 over, is going to be about 2 epsilon, 4 epsilon, something like that. Okay, so it's just a Markov inequality. Okay, so this is the main claim. Once we have this claim, we have sort of argued that if we pick all vertices with large degree, they will form a clique, and the number of such vertices is large. So let's prove this, and then we'll do the second half of the proof. So one thing maybe to point out is that this proof, it's not just a combinatorial statement. It is there's some algebraic content to this statement. That's one part of it. And some of you had asked me yesterday, why aren't we doing the lines test? And I said yesterday that it's hard to fit the lines test in whatever time we have. But you will see that in the proof of this claim, we will use something that's very special to planes, and it doesn't work for lines. So the lines test have to do something else as of now. Okay, good. So do people see why this may be true? So let's prove the claim. So we have two planes such that G pi and G sigma are inconsistent with each other. I want to claim that one of them must be, at least one of them must be inconsistent with many, many other planes. Yeah. Yeah, so if, if you have planes where the test passes and they intersect, they are going to be consistent. Yeah, they are consistent. No, but maybe on one of them, the test doesn't pass, right? I mean, consistency is G pi and G sigma have to agree on pi intersect sigma. So, yeah, so parallel planes are by default consistent if G pi, if the test passes on them. Okay, so yeah, so why would this be true? Why, if you have two planes that are not consistent with each other, you want to say that one of them, at least one of them, is going to be inconsistent with many, many other things. Is there a picture? Bad picture, but picture. So this is one plane. Maybe this is another plane. So this is, let's say pi, this is sigma. If they don't intersect, then yeah, then they're by default consistent. So let's say they intersect. If they intersect, they're going to intersect on a line. And if G pi and G sigma don't agree with each other on the line, it means that they are not going to agree on a lot of points on the line. Right? So G pi and G sigma, they are low degree polynomials. We are looking at the restriction of them on the line. So they are low degree univariates. They don't agree with each other, which means they will disagree on at least q minus k points on this line. Right? So there's a whole bunch of points where they disagree. So maybe these are the points. Now let's take any plane that intersects this line at one of these points. So maybe this is another plane. And this plane somehow cuts this line at one of these points where G pi and G sigma disagree with each other. Then the bivariate polynomial on this plane, the plane polynomial for this plane, will disagree with at least one of G pi or G sigma at this intersection point because they don't agree with each other. Right? Is that okay? Good. So the point is that there are many of these points where G pi and G sigma are inconsistent with each other. So any plane that intersects this line at one of these points of disagreement between G pi and G sigma will be inconsistent with at least one of pi or sigma. Yeah, how many planes do we expect? So what fraction of planes will intersect this line at one of these locations? What would you guess? So there are planes that will just not intersect the line at all. Right? So what fraction of planes will intersect the line at one of these points? Right. So a guess to make would be 1 minus, so the fraction of planes intersecting at this point should be something like q minus k over q. There are q points on this line. We are interested in planes intersecting some a subset of size q minus k. This is a reasonable guess. The problem with this is that not all planes are going to intersect this line. But if we discard the planes that don't intersect the line at all and look at all the other planes, the number of planes passing through each of these points should be the same. There's no reason for them to be different. So amongst those planes, this is the fraction of planes that will intersect at these points of disagreement. Now you can so add a little of 1 here. So you can convince yourself that the fraction of planes that don't intersect this line at all are small. They will go into the error term. Is that okay? Yeah. Okay. I don't want to do the calculations, but it's not hard to do. All right. Okay. So what we have argued is yeah. So I mean so if there is a plane that intersects this line at one of these points, then it has to be inconsistent with at least one of phi or sigma. So at least one of them must be inconsistent with these many planes. Okay. That's it. So that's the proof of this claim. And this implies that if we pick all the large degree vertices, all the vertices whose degree is 1 minus half times 1 minus k over q minus little of 1, fractional degree is large, then they will all be adjacent to each other. They'll all be consistent with each other, and they'll form a clique in this graph. Okay, and the number of those vertices is large. That's just a consequence of the average degree being large in the graph. Okay, so are we all sold on this? Questions? Okay, this is not the only thing I'm going to hand wave my way through today. But yeah, this is the easier one. We are good so far? All right. Okay, so yeah. 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 Yes, that is. Yeah. Yeah. Most of the planes will miss. Yeah, they are likely to intersect. Okay, good. So for the rest of this discussion, we'll focus on this clique. So let's say that so U is the subset of V such that U forms a clique. Size of U is large. It's at least 1 minus 10 epsilon times the size of V. So one thing I should say is that yeah, I mean there are these numbers I'm writing. I realized today morning that I did make a mistake in these numbers in the when I was working out the proof. So there's a very good chance we'll have to adjust some 10s and 7s. So yeah, I mean just be careful about it. Okay. So now I mean our goal is to take this large set of consistent planes and find a low degree polynomial that agrees with the plane polynomial on all of these planes. So we are going to do it in a few steps, okay? And there's a definition that's going to be important here. So this is the definition of so planes in general position. Okay, so planes pi 1, pi 2 to pi t are said to be in general position. If a few things happen, so every pair intersects at a line. So there are no parallel planes. Every triple intersects at a point. And no 4 of them intersect. Okay, so set of planes is, we'll say that they're in general position if every pair intersects at a line. If we pick any 3 planes in the set, they intersect at a point and no 4 intersect together. And I mean, there's nothing special about planes in general position. We could have defined, yeah, you could in general define hyperplanes in general position the same way in whatever dimensional ambient space you're working. Okay. So we have this set, this large set U of planes. We want to find a subset of planes in U that are in general position. And having these planes in general position will make our life easier in our goal to find a low degree trivariate that agrees with all the planes in the set U. So the claim is that, make it lemma, is that there exist maybe 10 times epsilon times q planes in general position in U. Okay. I'm discarding, yeah, I'm going to focus on these. We will come back to, we'll return to the set U at the end of the proof. But yeah, in order to find the polynomial, I'm just going to focus. In fact, it will agree on U everywhere. That requires a proof, but we will have to prove that. In fact, I'm going to also discard this set, and I'm just going to focus on some k plus 2 planes or k plus 3 planes inside this set. But for now, the claim is that there exist 10 epsilon q planes in general position in U. How many planes, how many planes does U contain? U has something like 1 minus 10 epsilon times q cube planes. Q cube is the total number of planes in 3 dimensions. So U has a huge number of planes. We are claiming that there is a small set there that of planes that are in general position. Okay. Okay. Does this seem believable? It seems believable, right? Yeah, I agree with this. It's a surprisingly yeah. I mean, there's a very weird proof that we have for this. So last week I thought I had a proof of this. How does one prove a statement like this? So given this statement, one of the first things to try is to pick planes at random and argue about it. I thought that worked. Yeah, but there was a bug in that argument. The other thing one could do is to try and pick planes greedily. So pick a plane, pick another plane, pick planes that are that don't violate the properties and so on. Swastik thought that worked, and yeah, there was a bug in that also. So right now the proof for this that we have is it is a true statement, but it's annoyingly indirect. So I don't know if I want to do the proof or I want to make it a homework problem. A lot of people asked about homeworks. Also, we know that greedy can't work. So there are greedy configurations that are much smaller than what we need here that cannot be extended anymore. Random, we don't know it wouldn't work. We don't know how to make it work. Okay, so let's do the following. Let's believe this lemma and proceed. If we have time, we'll come back and prove it, or I'll tell you something about how the proof goes. Otherwise, this goes in homework. Okay, so let's call this set, so let's say U naught is the subset of, or U hat is the subset of U in general position. and the size of u hat is 10 epsilon q. So why are planes in general position good for us? So they're good. So we'll get to that in a moment. But what I want to do, so remember, our goal is to find a low degree polynomial P that agrees with all the planes in U. So we will in fact focus on a smaller subset of U hat. So let U naught be a subset of U hat such that the size of U naught is K plus 2. The same K. K is the degree parameter everywhere. Okay. Okay. So here's the reason why we are trying to work with planes in general position. So lemma, call it 2 or 3, is that so any set of K plus 2 planes in let me write it differently. Okay, so let's define the set S to be pi I intersect pi j intersect pi k pi L, such that pi I, pi j, pi L are in U naught and distinct. So U naught is a set of K plus 2 planes in general position. You'll see in a minute. So we have to get our hands on a polynomial. We will define the polynomial just based on U naught. And then we will show that it's consistent with U hat and it's consistent with everything in U. And why a set of size K plus 2, that will be clear in a moment. So we are looking at the set U naught of K plus 2 planes in general position, which means any 3 planes in this set determine maybe I need K plus 3. So intersect at a point. So let's look at the points of intersection that you get from taking 3-wise intersection of these planes. So then S is an interpolating set for trivariate degree K polynomials. So let me say what this means. This means that so this is the same as equivalently. So for every function h from S to F, there exists a polynomial P of xyz degree K such that h of alpha equals P of alpha. This for all alpha in S. All alpha. So this says that the set S is a set of points living in the three-dimensional space. We go to each of these points and write an arbitrary value there. Okay. Then there is a polynomial P of degree at most K that will take this value at these points. That's what an interpolating set means. Is the statement clear? Okay. All right. The property of being an interpolating set is it's a non-trivial property. Tell me a set of points in, let's say, 2 dimensions that is not an interpolating set. For degree K polynomials, bivariate polynomials. 3 points will not work. K plus 1 points will work. Yeah. Good. So, okay. So I think let's sort of stay with this and reflect on it for a moment. So certain things should be clear. Suppose For given a function h, I want to find a polynomial p that satisfies these constraints. So these are like linear constraints on the coefficients of p, right? So the first natural thing to try is to maybe look at this linear system and solve for it. That's how you find p. The problem with this linear system is that it's a non-homogeneous linear system and it may not have a solution. Interpolating sets S are sets for which this linear system always has a solution regardless of what the function h is. The matrix is full rank. So if you open up the linear system, the matrix you get is full rank. That's what interpolating set means. If we were working with univariate polynomials, oh, by the way, the other thing to check is that the size of the set S is right. So we are looking for a polynomial p of degree k in 3 variables. So it has k plus 3 choose 3 coefficients. Right? I should say there exists a unique polynomial in fact here. So it has k plus 3 choose 3 coefficients. In order to find p, we should have at least k plus 3 choose 3 constraints. The size of the set S is exactly k plus 3 choose 3. So it passes that sanity check. If we were working with univariate polynomials, any set of size k plus 1 is an interpolating set for univariate polynomials of degree k. For bivariate polynomials, this already stops being true. And one example was if you pick k plus 1 points on a line, that's not an interpolating set for degree k bivariates, even though the number of constraints we are imposing is much less than the number of variables available to us. The number of variables available in a bivariate polynomial of degree k is k plus 2 choose 2. And we are only imposing k plus 1 constraints. But yeah, but you can show that you can come up with functions h such that there is no polynomial of degree at most k that agrees with these values on this. K plus 1, k plus 2, right? K plus 2 points. Okay, is that good? Great. So now we'll follow the theme of this, this particular lecture and not prove the lemma. I will either prove it or make it a homework. This is not hard to prove. This is actually relatively easy to prove. Great. So let's. This is the p that we are going to work with. We have to get our hands on a trivariate degree k polynomial which satisfies a whole bunch of properties. This is how we get our hands on the p. Okay, Varun, this answers your question. Why focus on k plus 3? Great. So okay. So now what remains to be done is to show that this p has agreement with a whole bunch of things. In fact, all planes in pi, all planes in U agree with. For all planes pi in U, G sub pi agrees with p on pi. So we will start by showing that, we have a sequence of subsets here, right? So there is U naught, which is the set of size k plus 3, and then there is U1, or what did we call it? U hat, which is a set of 10 epsilon q planes in general position. And then we have U, which is, so this is k plus 3 planes, this is 10 epsilon q planes, and this is 1 minus 10 epsilon times q cube plane. And we have defined p just using U naught. We will argue that, we'll first argue that p agrees with the plane's polynomial for every plane in U hat, and then we will argue that it agrees for the plane with the plane polynomial in every plane in U. Okay. Great. Questions so far? Okay. Okay. So let's start by arguing that planes in U hat are for planes pi and U hat, G pi is consistent with P. So, claim 1, that for all pi in U hat, G sub pi equals P restricted to pi. Okay. Is this clear? Is the first part clear? So maybe the first thing I should have proven is that for every pi in U naught, G sub pi equals P restricted to pi. We have defined P here. It agrees with all the planes polynomial for planes in U naught. This should be easy to see. Is this, how does one see this? Good. Great. So let's do this argument because at least the U hat argument is going to look very similar. So let's look at a plane pi in U naught. The set U naught has k plus 2 other planes. Let's look at the intersection of those k plus 2 planes on this pi. Okay. So consider pi I intersect pi for pi I in U naught minus pi. So we are going to get a bunch of lines, right? Every intersection is going to be a line. In fact, it's going to be a distinct line because planes in U naught are in general position. Okay, what do these lines look like? What can we say about the lines? These lines are also in general position in the sense that any two of these lines are going to intersect at a point and no three lines are going to be concurrent. Right? So all these lines are in general position. So this is, there are k plus 2 lines in general position. And we are focusing on a plane. We have k plus 2 lines in the plane on a general position. Let's look at the intersections of these lines. So let's say S, let's say T is the set of intersections of these lines. Okay. What is the size of T? What is the size of T? K plus 2 choose 2. There are k plus 2 lines, they're in general position, so any pair will give you a distinct point. So this is k plus 2 choose 2. Moreover, on all of these points, on all points on the set T, the polynomial P agrees with G sub pi because that's how the definition went. So for all alpha in T, the polynomial P at alpha agrees with G sub pi, G of alpha. The polynomial P at alpha, we should really think of this, consider the trivariate polynomial P. Look at its restriction to the plane pi. This is a bivariate of degree k. And this bivariate evaluated at alpha agrees with G sub pi of alpha. Okay. So we have two bivariates. We have G sub pi and we have the restriction, the bivariate you get by restricting P to the plane. These bivariates agree with each other on all alpha in the set T. And the set T is a set of intersections of k plus 2 lines in general position. So this lemma was stated for, this lemma was stated by taking intersection of planes. So we were working in 3 dimensions here. But this statement is more general. This is also true, for instance, for lines in general position. So the version of this lemma that's true is that if we take lines on a plane, if we take k plus 2 lines in a plane and look at the set of points, k plus 2 lines in a plane in general position, look at the set of points you get by pairwise intersections, that's an interpolating set for degree k bivariate polynomials. Okay, so what we are arguing here is that the set T is an interpolating set for degree k bivariates, and the degree k bivariates of degree k bivariates, and G sub pi and P restricted to pi are 2 degree k bivariates that agree with each other on this interpolating set. So because of uniqueness, they must be the same. So this implies that G sub pi is equal to P restricted. So the trivariate polynomial P is consistent with every plane in the set U naught. Okay, are we good? So I just want to finish this here. Okay, so far we have the definition of P and we have agreement with every plane in the set U naught. Now we want agreement with every plane in the set U hat. So let's write claim 2. For all pi in U hat, G sub pi equals P restricted. right? Intersect. Yeah, take the intersection. Yeah. Right. For bivariates of degree k. So the bivariate given by p, the restriction of p to pi and g sub pi, they agree with each other on an interpolating set, so they must be the same. Okay. What changes between u naught and u hat? Where in this argument did we use the fact that we had yeah, basically nothing changes. I mean, the same argument we did will also work if you take a pi in u hat. So if we take a pi in u hat, we again we are going to intersect it with planes in u naught. This is going to give us a bunch of lines. They are going to be in general position because u hat was in general position. And the number of lines is now actually going to be k plus 3 because we have the size of u naught is k plus 3. So basically the same argument that we did here will actually work for u hat as well. Is that okay? We are strongly using the fact that planes here and planes here are in general position. The same p. I mean, the claim is for the same p. All the claims will be for this p that was defined just using u naught. Okay, so what's that? So let me say it out. I see some puzzled faces. So take a plane pi in u hat. So let's focus on this plane pi. Okay. Now let's look at the intersection of pi with every plane in u naught. This is going to give us a bunch of lines. How many lines? Well, size of u naught many lines. So k plus 3 lines. Yes, we have defined a p. We had this part already used the fact that we had a p. Yeah. So we are on the plane. We are intersecting it with planes in. We are on a plane pi. We are intersecting it with planes in u naught. We have k plus 3 lines. They are going to be in general position because u hat was in general position. So we have k plus 3 lines in general position on a plane. And the restriction of the polynomial p to this plane agrees with the plane polynomial at each of these intersection points because all the planes were consistent with each other. We are using the fact that u was a set of pairwise consistent planes. And so again, you have two bivariates of degree k agreeing on an interpolating set for degree k polynomials. They must be the same, and so p is consistent with g sub pi on the plane pi. Okay, so same argument, nothing really changed. Yeah, we only had more degrees of freedom here. Good. What about this argument doesn't work if we want to extend it to u? The set u is not in general position. This is not a set of planes in general position. So I can't, yeah, we can't quite do the same argument. So how do we, so what do we do? So again, I mean, we should try to do the same thing and see what really goes wrong. So we take a plane pi in u. Now let's look at its intersection with planes in u hat, because why not? I mean, we have the condition on u hat. So we are going to get a bunch of lines. What is guaranteed to us is that if we look at the points of intersection of these lines, at those points, the restriction of p and the plane polynomial agree. But the point set that we are getting now need not be set of points in general position. That's the only part that breaks down. But I mean, we are working with low degree polynomials, and it's quite likely that Schwarzschild lemma should show up at some point, and it will show up here. The polynomial g sub pi and the restriction of p to pi will just have enough agreement that they must be the same because of Schwarzschild lemma now. So we'll just argue that you're going to get enough points on the plane that this will take care of. So claim 3 is that for all pi in u, g sub pi equals p restricted to pi. Okay. So this part of the proof, this is different from what happened earlier. So let's try and work this out. So consider a pi in u. And let's look at, consider the lines pi intersect pi I or pi I in u hat. This is a bunch of lines. So claim is that for all, or subclaim is that for all alpha in, let's call this L sub pi, so for all alpha such that, define this slightly carefully. So L sub pi is the set of lines, and let's define a set of points. Let's call this M pi. This is the set of points on lines L in L pi. Okay, so we are taking this plane pi, we are intersecting it with all the planes in U hat, and let's take the points that you get on these lines. And the observation is that so for all alpha in M sub pi, if we restrict P to pi and look at the evaluation at alpha, this is going to be equal to G sub pi of alpha. Is that clear? This is a line, the point alpha comes out of the intersection of pi with some plane pi I. We have already argued that P and G sub pi I agree with each other everywhere. And any of these points alpha in M sub pi is actually a point on one of the planes on which we know that P and G sub pi agree. Right? So this is just a consequence of the previous claim. Okay, great. So these are two bivariate polynomials of degree at most k. They agree on all points alpha in M sub pi. If the size of M sub pi is sufficiently large, they must be equal to each other by the Schwarzschild limit. So what can we say about the size of M sub pi? What about the size of L sub pi? How many lines are there? Is it 10 epsilon q? Can two lines be the same? That's not clear? Yeah, that's not clear. So it's, I mean, an easy argument will show us that the size of L sub pi, L sub pi can be as large as the size of U hat, right? It can be as large as 10 epsilon q. It can't be any larger than that. But can it really be 10 epsilon q, or can it be smaller? So we'll argue that it should be at least the size of U hat by 2. Right. So why? So the argument is that, okay, so what are we really trying to understand? So we have this plane pi, we are intersecting it with a bunch of planes in general position. We are getting lines. We want to understand, can you get the same line by multiple intersections? You can get the same line by 2 intersections potentially, right? Because you have pick two planes pi 1 and pi 2 in U hat. They intersect at a line, take that line, and maybe the plane pi passes through that line. So a line can be, you can definitely get a line by, pi intersect pi 1 may equal pi intersect pi 2. That's possible. Can you get a line, can 3 of these intersections be equal to each other? 3 intersections can't be equal to each other. If pi intersect pi 1 equals pi intersect pi 2 equals pi intersect pi 3, then it means pi 1, pi 2, and pi 3 must intersect in a line. But that violates the general position definition. So you can get, so you may have collisions, but we will not have collisions where 3 planes collide. The collisions will be at most 2 at a time. So the size of L sub pi is at least U hat over 2. What about M sub pi? So we know we have a bound on U hat, so this is at least, let's say this is 5 epsilon q. What can we say about M hat? So we have 5 epsilon q lines, and we are looking at the union of points on these lines. How large should this be? So the size of M sub pi is at least what? How do we do this? U L pi by 2. Good. We can do that. Yeah, I think that would be sufficient for us. Yeah. We could have done inclusion exclusion, right? We have a set of lines. We are taking the union of them. Two lines will only intersect at one point. So we could also do that. So there are 5 epsilon q lines. Each line contributes q points. And there are 5 epsilon q choose 2 pairs, and each pair can contribute at most 1 point. So you get something. Just to get a sense of these numbers, so 5 epsilon q squared minus this is 25 by 2 roughly epsilon squared q squared. Right? There's an epsilon q squared here, there's an epsilon squared q squared here. So this is at least 4 epsilon q squared for epsilon small enough. Great. So we have 2 bivariate polynomials of degree at most k that agree on 4 epsilon q squared points. So yeah, so by the short-zipper lemma, if p restricted to pi and g sub pi are distinct, then their agreement, the number of points of agreement, has to be at most what? At most the degree times q, which is k times q, and k was like epsilon q. So this is at most epsilon q squared. So if p restricted to pi and g sub pi were distinct polynomials, their agreement should have been bounded above by epsilon q squared. But we just argued that they agree on 4 epsilon q squared points. So they must be the same. So implies that g sub pi must be the same as p restricted. So that's it. So that completes the argument. Questions? So that basically completes the proof. Modulo the proof of some lemmas. Yeah, which I'll decide in the next 30 seconds if you want to do it. Questions so far? Yeah, what doesn't work for line system? Great. So we had a lemma 1 there where we said if 2 planes are inconsistent with each other, then at least one of them must be inconsistent with many other planes. That used something. It used the fact that if 2 planes are inconsistent with each other, then the bivariates will disagree on a line. And on a line, you have distance. And we used that distance. We said if they disagree, they're going to be different. They're going to be disagreeing on many points on the line. So you get a lot of planes on which have to be inconsistent with at least one of them. So we're using the fact that evaluating a low degree polynomial on a line gives you distance. And a line is what you get by intersecting 2 planes with each other. If you intersect two lines with each other, you get a point. You don't get distance. So that's one concrete place where this argument doesn't, it uses the fact that we have planes whose intersections have distance. Other questions? Yes. Yeah. Yeah, random bit deletion, at least I couldn't make it work. I thought it worked, but yeah, but maybe it works. Other questions? What about this works for, oh, planes intersecting, etc. I mean, the fraction of planes we were getting there was almost everything. All of these things require. No, it's a different argument. It will, like in higher dimensional space, a line and a plane will just almost never intersect. So this place where we said almost you get inconsistency with almost half the, yeah, so that doesn't work. Great. Well, then the distance, I mean, then you do get distance. So that argument can be made to work. Yeah, exactly. Instead of just doing a Reed-Solomon thing, we will do a Reed-Muller code with on m-2 variables. So that argument can be made to work. Other questions? Okay. So K was epsilon Q, but I think K can be pushed higher with some care at a few places. I'll have to think a little. But I think, yeah, I mean, we are being very conservative in taking K to be epsilon Q. Yeah. Other questions? Okay. Okay, so then we push the lemmas to homework. Maybe let me say something about the lemma. So there was this lemma about planes in general position, right? So lemma 2 was that there exist n epsilon q planes in general position in U. So the way this lemma, at least the only way we know how to prove this right now is, so we will, and U was a set of large size in the set of all planes. So the way we can prove it is we have a clean algebraic construction of planes in general position. So we'll take Q planes in general position. I'll describe the construction in a minute. And then we'll take these planes and we'll take a random rotation and translation of these planes. Okay, so or let's just do a random rotation of these planes. So a random rotation of these planes in general position will continue to keep them in general position. But since the rotation is random, you're going to hit the set U at roughly the right number of planes. And the set U is super large. So the plan is, so take a, take a nice construction. Of such planes, and basically do a random rotation. That is going to give us enough planes in general position. What's the nice algebraic construction? So how do we describe planes? One way of describing planes is I give you a normal vector and a translation. So a plane pi can be described by a vector v and a translate lambda. So this is the set of all points, let's say ABC in FQ, such that AV1 plus BV2 plus CV3 equals lambda. One parameterization of it. So let me give you the initial construction of the planes. So pick, okay, so let me define V of V comma lambda of alpha to be rather. So let's say V of alpha is the vector 1 comma alpha squared, and lambda of alpha is alpha cube. Okay. So the set of vectors we are going to construct, we are going to pick alpha in FQ and collect V lambda and V alphas and lambda alphas. This is a collection of planes. There are Q of them. You can see that they are all distinct. And you can argue that they are in general position. And you take this collection and then you do a random rotation. You can argue that that has the properties we want for that level. Okay, I don't want to say more. Okay, so this will, so I'll put this in a homework and it over. So let's change tracks a bit and talk about list decoding. That's going to be the theme for the rest of today's lecture and tomorrow's meeting. So far we have seen unique decoding of codes. And the idea in that discussion was that if we take a code of distance delta and we take a Hamming ball of radius delta over 2 around any of the code words, these don't intersect. So if you give me a received word that is at most delta over 2 far from any code word in this code, then in principle the code word is uniquely defined, and for some nice codes we can also find this code word efficiently. So sort of the main question here is to now increase the radius of this ball to be larger than delta over 2. So now we are going to look at code words and draw a ball of Hamming ball of radius larger than delta over 2 and try and understand what happens. So what might happen now is that these Hamming balls might intersect each other, right? Which means that if I take a ball of radius rho around all the code words, these balls may be intersecting, which means that there may be, or if we draw a Hamming ball of radius rho around all points in the space, then many of these balls might contain more than one code word. So this the unique decoding property is no longer true. Yeah, but I mean, it's a natural combinatorial question to understand what really happens beyond that. So let's have a definition, and then it will make it easier to talk about things. We'll say that a code C is rho comma L list decodable if so for all A in sigma to the n. C is a subset of sigma to the n. If you look at the Hamming ball of radius rho times n around the point A and take its intersection with a code, the number of code words in this ball may not be unique, but it's no larger than L. So far, we have been working with codes that are delta over 2 comma 1 list decodable. That's the unique decoding regime of parameters. Now we would like to have we would like to take rho to be larger than delta over 2, and L, and we will have to live with L potentially larger than 1. Is that okay? So that's the definition. Great. So given this definition, there are many questions we can ask, right? For instance, when we defined the rate and distance of the code, we wanted to understand what are the right trade-offs between rate and distance. Given a particular distance, what's the maximum rate we can have? What's the maximum rate we can achieve? We can ask the same questions here. If we fix the parameter rho and L to be something, what's the largest rate of a rho L list decodable code that we can hope to have? And what kind of constructions do we have? So what is the largest rate that we can achieve via a construction? Then we can look at our favorite codes and ask, well, are they list decodable with interesting regime of parameters? Can we take rho to be larger than delta over 2? And does L become exponentially large immediately, or there are interesting things to be said about this regime of parameters, right? And yeah, so there are many nice questions. Okay, so let's try. So in the first lecture, Swastik proved an upper and a lower bound on the rate distance trade-off of for codes. We said if the distance is delta, rate can't be larger than blah, and we have codes that give us rate at least something. So let's prove similar statements for rho L list decodable codes. So theorem. So if decodable, then rate of C is at most 1 minus h of rho minus something like log L over n. Don't remember, there's a constant here. Okay. So this is an upper bound on the rate of a code that's rho comma L list decodable. if you take L equals 1 and rho equals delta over 2, we get what we were getting earlier. We can ask the question in the other direction, saying what's the best row rate that can be achieved for a code that is rho comma L list decodable. There's another theorem here. It says, so there exists rho L list decodable codes C with rate of C being at least 1 minus h of rho minus 1 over L. Okay. Great. Oh, binary, I should have said, yeah, good point. Maybe this has to be L plus 1 for it to make sense. Yeah, for this discussion, we are over the binary alphabet. Otherwise, oh, this was fine. Here, so here I should have said 0, 1 to the n at both places. Yeah, otherwise there are similar statements, but these quantities have to be replaced with appropriate Q-array analogs. Good. All right. There's something surprising about these statements. Tell me what it is. I mean, we have seen similar statements in unique decoding, in the unique decoding setup. Compared to that, there is something surprising about this. Yeah, I mean, if you look at these terms, they are the same at both places. This was not the case for the unique decoding setting. For the unique decoding setting, this was delta over 2, but this was h of delta. So there was a gap. So the gap is here in sort of the lower order term in these inequalities. What is? H. Oh, H. H is the binary entropy function. So H of rho is so rho this is log base 2. Here 1 by 1 by log L. We'll try to prove this and maybe figure out that. Yeah. Okay. So yeah, so maybe this term might be 1 over log L. Are we good with the definition and the two statements? Okay. Should we try to prove one of them? Let's prove one of them. We have not proven a whole bunch of things today. Let's try to prove the first one because we don't know what the term is. So we have a rho L list decodable code. We want an upper bound on the rate of the code. How do we do this? We have done this for unique decoding. Basically do the same thing, right? So, but now the issue is that if we draw a ball around every point in 0, 1 to the n, this ball of radius rho n, this is going to contain more than one code word. Yeah, okay. So, and how many code words how many balls can a single code word participate in? Okay, so yeah, I mean, let's draw a graph and do some counting here. So this is the set of all points in 0, 1 to the n. This is the set of all code words. And we'll join an edge between a point and a code word if this code word lives in the ball of radius rho n around this point. Okay. Let's count the number of edges in this graph one way and the other. So the number of edges . it's at most something. What's an upper bound on this? It's at most 2 to the n times L. For the degree of any point here can't be larger than L. It's at most 2 to the n times L. But if we do the count on the other side, so what's the degree of this, what's the degree of a code word in how many of these points in this space can a code word be adjacent to? Right, so a code word can only be adjacent to points here that are within a distance of rho n from this code word. Right, so the degree on this side, somehow we seem to be doing two upper bounds. It's an equality. Right, the other side is an equality. So number of edges is equal to the size of the code times b of rho n. Right, it's going to be adjacent to everybody in a radius of in the Hamming ball of radius rho n around the code word. Okay, so now we compare these two things. So this means that the size of C times b of rho n is at most 2 to the n times L, which means size of C is at most 2 to the n times L divided by b of rho n. So what's the rate of this code then? So rate is, this is log base 2 of the size of C divided by n, which is n plus log L minus log of b rho n divided by n. What is this quantity? This is h of rho. So this is h of rho times n. So this is n plus log L minus h of rho times n divided by n. So it's 1 minus h of rho plus log L divided by n. Okay, so log L by n. Oh, it's a plus. Add a plus. Okay. Okay, so the second theorem, you want to guess how it's proved? We have seen a unique decoding statement of a similar flavor. Pick a random code, argue that, yeah, it has the properties that we want. So we'll not prove that. Question? We are past time. Right, great. Okay, so we'll stop here. We'll continue from here next time. So the plan next time is to continue more discussions on list decoding.